All right, question number 39. We have a toy gun, sort of like what you had in the lab, and when it is loaded, you would be looking at picture A, because you see the spring is compressed. The load is a certain distance, which is x down. Mind you, when you talk about potential gravitational energy, it is up to you where you decide the zero level is. So just let's say that this is 0. So at the moment right here, when the gun is loaded and nothing is moving and only spring is compressed, we're going to talk about potential elastic energy at point A. In the situation called A. And then neglecting all resistive forces, they give us all the values. They give us compressed distance of the spring to be 0.12 meters, so 12 centimeters over here. This X is 12 centimeters. Then we also have the mass of the load, which is 0.02 kilograms, as we have to have it in kilograms. And then the gun can launch the projectile from rest to a maximum height of 20 meters above the starting point of the projectile, meaning that we do not have to figure out that it's 20 meters above this X. It's not 20 meters over here, but 20 meters from this point right here. Hence, it makes sense to call this your zero level for potential gravitational energy. Describe the mechanical energy transformations that occur from the time the gun is fired until the projectile reaches the maximum height. So you would say for A, elastic energy, initial, it turns into kinetic energy, midterm, so to speak. And then you have potential energy, gravitational. And in the end, kinetic energy also turns into gravitational, and that is all we have. The spring is decompressed, no potential elastic energy left. Kinetic keeps turning into gravitational, and eventually all of this becomes gravitational. Determine the spring constant. That's our question B. Well, we're going to latch on this elastic initial equals gravitational final, because any change in elastic, so I would say change in elastic plus change, that shouldn't be initial. So I could also say that change in elastic plus change in gravitational equals 0, because there's no air resistance. They told us to disregard everything. So that's how I would say elastic final minus elastic initial plus gravitational final minus gravitational initial would be equal to 0. Now, mind you, this was 0. This was kx squared initial over 2 plus this is mgh final. This is 0 equals 0, right? And that is how we have the right to say that mgh, and that is how we have the right to say that mgh final equals kx initial squared over 2. And from there, we just plug in the numbers and figure out our spring constant as k will be equal. Remember, we cannot cancel mass as we like when it goes to gravitational kinetic. So it will be 2 mgh final, which is our 20 meters, over x initial squared. In C, we want to find the speed of the projectile as it moves through the equilibrium position of the spring, where x equals 0 as shown in the figure. We need to make sure that we realize that our elastic initial turned into kinetic final plus gravitational final. We need to make sure that we include the fact that our little load went up 12 centimeters above where it started. So therefore, I'm going to say that my kx squared initial over 2 mv final squared over 2 plus mgh final, and that technically is x initial, because the value is the same. It went up by 12 centimeters and the spring was compressed by 12 centimeters, from where you're just going to multiply by 2 to get rid of the denominator. So I'm after v, so I'm going to grab this, put it on the left, so I end up with kx initial squared minus 2mgx initial. I would divide all of that by m and root that. That's one way. Your other way is to realize that if I look at here, gravitational final is just mg times 20 meters. And I could say that right here, this level is all kinetic energy final. Then if I say that this also has u gravitational, if you call this 0, then that height I need to subtract minus 0.12. It's not going to be that big of a difference, but it will be a little bit of a difference, so we should account for it. We will check if we have the identical answers. So let me give you the alternative again. U gravitational final will be kinetic energy initial. So I will do mgh final minus mv initial squared over 2. Then mass cancels, and I end up with 2gh final over, no, not over anything. So it's going to be just the root of 2gh final equals my v initial. If I root that, I'm going to go ahead and figure out what my k is by doing this. So I got my k as 2mgh final over x initial squared. Write out everything, cancel some powers, and I end up with 544 newtons per meters. Let's go back here. So therefore, I'm going to have the root of, I'm going to factor out 0.12 because it's twice here. So it's going to be 544 times 0.12. Then I have minus 19.6 times 0.02 for mass, parentheses, and then over 0.02. I could technically do 0.02, so it's going to be 6. But anyway, it is 19.7 meters per second. And if I use this method, it's the root of 19.6 times 19 point, so I'm subtracting 20 minus 0.12, 1982, 19.7 again, 19.7 meters per second.